Right, this is page 130 of the Incredibles notebook. We're looking at the mean value theorem for integrals. This theorem is not as well used as the mean value theorem for derivatives. At least it's not used in this form. Okay, it is used in this form, however. Right, this is the average value of a function. So if you look at this over here and you look at this over here, all right, they're related, right? So you got this b minus a over here. If I divide both sides by b minus a, I get this expression, okay? And what that is the average value. So they're saying there's this y value, there exists a y value that is the average value of that function, okay? That kind of makes sense. All right, now keep in mind functions are continuous, right? If you can integrate it, it's a continuous function, okay? So it kind of makes sense. It's not like if you have a set of grades, let's say you have a 75 and 100, the average between those two grades is like, okay, I chose bad numbers. Say 80 and 100, the average will be 90, but there is no 90 as a grade. So that's different, right? That's a discrete set of numbers that you're taking the average of. Here is a function, and you're finding the average of a continuous set of numbers. All right. So that, and this guarantees, by the mean value theorem, it guarantees that there's a one y value that is equal to the average value. All right. But we're more interested in just finding the average. So when we want the average value of a function, we on an interval. So we take the integral on that interval and divide by the length of the interval. All right. So that's pretty straightforward. as anything can be straightforward in calculus. All right. Find the average value of this on that interval. So we're going to go from 1 to 4. And we're just going to integrate that. 3x squared minus 2x dx. So when we integrate that, you add 1 to the exponent, divide by the exponent, right? So this is very nicely done because we're going to get rid of that 3. So that would be x cubed minus x squared, right? Add 1 to the exponent, divide by the exponent. So that 2 disappears too. And we're going to take it from 1 to 4. So you plug it in. 4 to the third is 64 minus 16. Plug in the 1. 1 minus 1. That's 0. So that's 48. And I forgot. I got to divide by 3. So I want the 1/3 here, 1/3 here, and 1/3 here. All right, and it's 1/3 all this. So that's going to be 16. Final value is 16. So I put the 1/3 out here, 1/3 here, 1/3 all that, right? 1/3 of all that, and I get 16. All right, and then it says find a value of c guaranteed by a mean value theorem for integrals for f of x. So we got it equal to 16. Is that right? Yeah. Yeah. We got it equal to 16. So when is this function equal to 16? 3x squared minus 2x. When is that equal to 16? Right? We're going back to the original function. When is that equal to 16? So it's 3x squared minus 2x minus 16 equals 0. Factor that. Would be 3x, x, 2 times 8, so 8 and 2. We want the 8 to be negative, so it's this way. And we want that equals 0, so it's x equals 8/3 and x equals negative 2. So that means the c that's guaranteed is 8/3. Right? Negative 2 is not in that interval. So that's it. Alright, number 5. Neglected to mention this theorem in page 291 of your textbook before I do number 5. Alright, there's a theorem called the Net Change Theorem. This actually comes after, so this is a good place as any to talk about this. It actually makes more sense to talk about it here, but the author of the textbook doesn't mention this theorem till later on, so I want to mention it now. Alright, the net change theorem goes like this. If I have a rate of change, if I'm given the rate of change, so I'm given the derivative of a function, okay, then if I integrate that between those two intervals, I get the actual net change of the function. Alright, so let's say I have a constant speed of 60 miles per hour. So this is the given rate, right? That's my f prime of x. So this is a pretty straightforward form, okay? And let's say I want to go from 1 p.m. to 2 p.m., okay? So that means it's integral from 1 to 2 of 60. And if I integrate that, that's going to be 60x from 1 to 2. So plug it in, that's 120 minus 60, that's 60. Okay, so I did something where you don't need calculus, but what I wanted to show you was that this confirms the calculus, right? If you travel for 1 hour at 60 miles per hour, you're going to go 60 miles. Okay, so that's the calculus working. For a very simple case, you're right, you don't need calculus for this, but I'm just showing you this to show that it confirms your common sense, that the calculus works. Alright, so now we're given this problem. We're given a rate. It's important here that we're given the rate, okay? And the tank is leaking at that rate. Alright, so when we graph, and it says graph the curve, so it's going to be at 100. So 100, and this is 200 over here, so this is counted by tens. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100 here. And it's 20 on this line. So this is counting by ones sideways, I guess, by ones. Well, it's 20 over here, okay? And it asks about 20 down here. So I'm going to just plug in 20 into this expression. When I plug 20 in there, I get, what's that? Negative 400 divided by 12 plus 100. And I get 66.6. Alright. So 10, 20, 30, 40, 50, 60, a little over. So I have a graph that basically looks like that. Alright. Okay. It hits peak over here, not over here. Alright. So that's the graph. That's part A. Graphing the curve. Alright. B, how much oil has leaked out by the end of the day. So by the net change theorem, how much oil leaked out by the end of the day would be 0 to 5 of that rate. So negative t squared over 12 plus 100 dt. Now this is a calculator problem, so I'm going to let the calculator do all the work. Okay, and this is an opportunity for you to know how to use the calculator. Okay, and so we're going to do, say, alpha, I think it's window, right? I'm looking for fn int. That's a numerical integration. So I press 4 for that. And I'm going from 0 to 5. And I know this function is in t, but I'm going to just change it to x. So it's going to be, let's go ahead and do this. Right? I forgot the negative sign, so it's negative x squared over 12 plus 100 and x. Alright, so that's it. We just have to calculate it. It's 496.53. So 496.53. And we're going to, what's that? See how much oil has leaked out between 5th and 10th day. So you do basically the same thing. You're just going from 5 to 10 instead. Negative t squared over 12 plus 100. And since you got it on the calculator already, all I'm going to do is go up here, get it, and edit it. So I just go scooch to the left. Oops. I went too far. 5. Nope. There we go. Delete that. 10%, and now it's 475.69. Alright, why is this answer less than in part B? Well, rate is slowing down as the day progresses, as the days increase. That seems like a good reason as any. Alright, what is the average daily loss for 20 days? So now we're going to go from 0 to 20, and we're going to divide by 20. Okay. So I'm going to go in here. Basically the same thing again. Take enter, and I'm going to go far left. Can I go further? I'm going to say 1. Ooh, bad idea. Okay. I forgot to hit the insert button. Alright, so go far left. Well, you know what? Instead of going far left, we could put this in. We just say divide by 20. Okay. After the dx, then it should be fine. Oops. Computer just blacked out. All right. Okay, from 0 up to 20. Come on. 2. All right. So note, I did put that divided by 20 down here. Okay, now press enter. And I got 88.89. So that's it. That's D. Okay, let's go ahead and close that out video.